Hi there, my name is Timo Groß and I'm happy to present real-time decision-making for a car manufacturing process using deep reinforcement learning. This is joint work with Joschka Groß and Verena Wolf. Let me start with the motivation right away. We are from Germany, and to be more precise, we are from the Saarland, which is the smallest county in Germany. The Saarland University is placed right here, and quite close to that, roughly here, there is a plant of the Ford Motor Company. In such a plant, usually, the production order is like this. First, the body of the car is created, afterwards it is painted, before it is then brought and stored in a line buffer, and in the last step, in the final assembly, all the pre-produced parts of the car are put together. In the beginning of this process, the optimal production order is determined. Unfortunately, there are many unforeseen turbulences during the production, altering the production order. But especially for the final assembly, the production order is crucial for the success in forms of how many cars can be produced per time unit. Therefore, the line buffer is the last chance to reorder the cars. Currently, this reordering is controlled manually by humans. Now that you have seen where our motivation comes from, let's now start with the different models. The first model we create is the so-called One Control Unit model, OCU. The line buffer consists of an input line where the cars that are about to be stored come in, an output line where the cars are taken out and brought to the final assembly, and several lines with the same capacity where the cars are stored. For the OCU model, one only needs to decide where to store the next car. In this example, the blue car with ID 2 would be stored on the second line. Then all other cars on the chosen line are pushed one further, and the first car is removed from the line and brought to the output line, where again all other cars are pushed one further. The last car, here with ID 7, from the output line is dropped. So the input line and the output line are always the same. Therefore, we assume that the buffer is always filled completely. When a car is taken from the input sequence, the other cars are pushed one further and the empty spot is replaced with a random new car. While you here see an example that is quite small, our model is completely parameterized. You can alter the number of different car types, as well as the length of the input and output sequence, and also the number and capacity of the lines in the buffer. For the Two Control Unit model, TCU, we drop the assumption that one always needs to insert and take out from the same line. Therefore, we need two different control units controlling where to store a car and where to take out a car from, respectively. We still refill empty spots in the input sequence with random new cars, but also drop the assumption that the buffer is always filled completely. The model is still completely parameterized with the initial parameter that tells us how many of the buffer spots are initially filled. Our objective that we try to optimize here is given by some rules of thumb. These are derived from reality, as currently the manual optimization in the plant is also done by following such rules. Each rule is car specific and consists of a distance and a penalty. The distance gives us the number of different cars that must be produced before the same type of car is allowed to reappear. The penalty is an integer number that reflects the time loss that occurs in the plant whenever the rule is violated. All rules can be checked by considering the output sequence only. Consider this situation for the Two Control Unit model. When now the decision is made to remove the car from the first line, the blue car with ID 2 would reappear quite closely in the output sequence, which would cause a penalty. Now that you have seen both of our models, let's have a look at the optimization. We use three different optimization techniques: reinforcement learning, a look-ahead search that approximates optimal decisions, and decisions based on heuristics. For deep reinforcement learning, we make use of deep Q-learning and algorithms we call Monte Carlo Research Expert and Monte Carlo Research Expert Plus. Before going into detail about the algorithms, Let's have a short look about the general principle of reinforcement learning. In deep reinforcement learning, our agent is represented by a neural network. It will then send a request about the current state to the environment, here our line buffer. The line buffer will answer with the current state, so the information which cars are currently placed where. The agent can then decide which line to proceed next. The environment will check whether a rule was harmed and answer with the corresponding penalty. This cycle is repeated multiple times. For the OCU model, this principle can be applied fairly easy. For the TCO model, there is not one, but two decisions to make. Therefore, we also have to train the two neural networks to make decisions. One for storing the cars and one for taking them out again. So when going back to our optimization techniques, we have to add another layer when considering the TCO model. We will present three different ways to answer the problem of multiple decisions for Q-learning: vanilla multi-agent, cross-product, and curriculum Q-learning. The most simple algorithm, the vanilla multi-agent Q-learning, tries to train two networks simultaneously. Without wanting to anticipate too many results, this is not working pretty well. The cross-product solution is answering the multi-decision problem by turning it into a single agent problem. Instead of having two agents, we create one agent that simultaneously decides both the input and the output line. This results in a quadratically increase of the action space. As deep reinforcement learning is known to not scale well with an increasing action space, we expect this solution to perform good on small instances, but to not be applicable to larger ones. Last, we apply curriculum learning. While usually a curriculum is given by repeatedly increasing the task's difficulty, we proceed with an iterative curriculum. In the beginning, we freeze the input agent and replace it by a random agent. Thus, we need to train the output agent only. Afterwards, we fix the output agent that was received in this training manner and train the input agent to create a line buffer that is better suited to take out the cars without receiving penalties. We iterate this process until we see no further improvements in the agent's quality. The Monte Carlo tree search approach can handle both the OCU and the TCO model. We construct a search tree. Instead of a classical rollout policy, as it is usually handled in Monte Carlo tree search, we save up the computation time by just taking the Q value of the networks we trained with Q-learning, our so-called experts, to evaluate the leaf nodes. For Monte Carlo tree search expert, we do so by replacing the cars at the beginning randomly. For Monte Carlo tree search expert plus, we perform a look ahead to check which cars will come in next. To evaluate the performance of our deep reinforcement learning approaches, we compare ourselves to established algorithms. The first one is what we call a look-ahead search that is based on the well-known planning algorithm A*. We compute a perfect plan for the given input window. That means a sequence of actions until all cars of the current input sequence would be inserted. That is guaranteed to be optimal. Then, only the first action is applied and the empty spot in the input sequence is filled with a random new car. We can then use the new information to again compute a perfect plan while still only executing the first action. This algorithm's performance and runtime both strongly increase with the size of the input sequence. Additionally, we compare ourselves to heuristics, which are inspired by the current manual control within the plant and which approximate human decisions. Their performance and runtime are independent from the input sequence length. Now that you have seen both how our models are constructed and how we tend to optimize them, we will present our analysis. For our experiments, we considered constantly 8 different types of cars, an output sequence length of 4, and a line capacity of 3. We varied the number of lines between 2 and 4, and the input sequence length between 1 and 9. In case of the TCO model, we considered a buffer that is filled initially with 60%. For each of these settings, we performed 1000 simulation runs where we inserted 100 cars each. Additionally to the results of the already presented algorithms, we performed the look-ahead search for the largest length of the input sequence that we could compute in reasonable time. This is the best approximation of the optimal result that we can provide. Note that this value is computed by making use of information that may not even be available in the real blend. The comparison is thus somehow unfair in favor to this value. It should more be considered as an upper border instead of a competing approach. Considering the OCO model with two lines, all of our agents DQN, MCDS Expert and MCDS Expert Plus do not only perform similar to the look-ahead search, but MCDS Expert for most of the experiments and MCDS Expert Plus even for all experiments outperform the look-ahead search. The performance of all of our approaches is quite close to the upper border, which was computed with look-ahead search 20. All of the heuristics are outperformed by far. The runtime on the first hand depicts a surprise, as the Monte Carlo tree search Expert has a slightly worse runtime than the look-ahead search. Our MCDS makes use of two termination conditions, the maximal number of visits and the maximal computation time per step. Whenever one of both criteria is met, the construction of the search tree is stopped and the action is chosen. For this small model, the computation time criterion was never met and therefore the runtime can be explained easily. The runtime of MCDS Expert is only slightly higher than the one of the DQN, which can be considered similar to the heuristics. The experiments with 4 buffer lines depict similar runtime observations, with the difference that here the computational time limit of the MCDS approaches can be observed clearly. Regarding the performance, there is a surprise. Not only do the MCDS approaches outperform the look-ahead search, but they even perform better than the result obtained with look-ahead search 12. Both approaches are that close to a penalty of 0 that the difference can be neglected. For the TCO model, we compare all of our multi-agent approaches, vanilla multi-agent DQN, here abbreviated DQN, curriculum learning and cross-product learning. We consider several combinations of insert and removal heuristics. The MCDS Expert and Expert Plus make use of the most successful DQN policy, which always was the curriculum learning one. Regarding the performance, one can see that vanilla multi-agent DQN seems to be unstable and also is performing worst of our approaches. The cross-product agent drops its performance when the input sequence increases, while curriculum learning and the MCDS approaches increase. What is a surprise here is that curriculum learning is performing better than MCDS Expert, as the latter makes use of the curriculum learning policy to evaluate the leaf nodes. Overall, we can be quite satisfied with the performance of our approaches, as we perform close to our upper border and outperform the heuristics that approximate the current status quo in the blend by far. The runtime of all of the presented approaches is quite similar here, so let's directly have a look at the 4 lines TCO model instead, as there the differences become more recognizable. Here we can clearly see why the look-ahead search is not applicable in the real blend. The runtime increases exponentially. We could not compute any solution for look-ahead search 9. The runtime of the MCDS approaches is limited due to the time termination constraint, while the runtime of the DQN approaches is independent from the input sequence length. Considering the performance, the problems of vanilla multi-agent DQN becomes vivid. The agents sometimes fail to learn the task at all, performing even worse than the heuristics. Again, the curriculum learning approach works better than the cross-product approach, while MCDS and MCDS Expert not only outperform the look-ahead search, but operate close to a penalty of 0. For the future, and as of today we partially already did this, we are planning to extend our experiments to include more buffer lines, a higher capacity of the lines, the real rules that are used in the blend, which includes to represent the cars by their features instead of their IDs. Additionally, we want to replace the rules of thumbs with a digital twin, a simulation of the final assembly to optimize the real delays instead of artificial penalties. And finally, of course, we want to bring our implementation back to the blend of the Ford Motor Company to optimize the line buffer in reality. To summarize, we have presented our first small model of the line buffer, which was inspired by the Ford plant in Saarlouis. We presented several reinforcement learning algorithms to optimize this buffer, as well as more classical approaches to which we compared ourselves to. We have shown that considering the combination of runtime and performance, reinforcement learning can bring real benefit to this real-world application, as it is performing close to the optimum while still being feasible.